Hello, chemistry students. Today we're going to talk about Gay-Lussac's law, and it's going to connect the relationship between temperature and pressure. This one occurs at a constant volume, so just keep that in mind. Again, we're working with temperature and gas, so we're going to be using the Kelvin temperature scale again, because 0 is set at absolute 0. Converting between Kelvin and Celsius is done using this equation. Gay-Lussac's law states that the pressure of a gas is directly proportional to the Kelvin temperature if the volume remains constant. So the volume has to remain constant, and the two are directly proportional. But you should remember what that means. So let's finish these two sentences together. At constant volume, if temperature is increased, pressure will increase. At constant volume, if temperature is decreased, pressure will So the mathematical formula that represents Gay-Lussac's law is P1 over T1 is equal to P2 over T2. This is where P1 is equal to the initial pressure, T1 is equal to the initial temperature. Then after the gas undergoes a change, P2 is equal to the final pressure. And T2 is equal to the final temperature. Now remember that these two temperatures are going to be measured in Kelvin. So here's a visual representation of Gay-Lussac's law, and the constant here is volume, and that's because these Erlenmeyer flasks are sealed with these stoppers. Now on the left, we have cold water representing T1, and on the right, we have boiling water representing T2. Now remember that pressure is the force when these gas molecules collide with the side of the container. So what this image is showing you is that there's the same amount of molecules, if you count them up on both sides, and they can't take up any more space because they're trapped in the space. So the pressure on the walls of this container is going to increase because you're adding energy to the gas molecules when you increase the temperature. A sealed cylinder of gas contains nitrogen gas at 1.00 times 10 to the 3 kilopascal pressure and a temperature of 20 degrees Celsius. When the cylinder is left in the sun, the temperature of the gas increases to 50 degrees Celsius. What is the new pressure in the cylinder? So the first thing that we need to find out is which law are we using, and we can do that by picking out the part of the sentence right here, a sealed cylinder of gas. That means that we have a constant volume, and we're going to use Gay-Lussac's law. What is the unknown? They're asking for the new pressure in the cylinder. So that is P2, and we just need to identify the things we do know. The initial pressure is 1.00 times 10 to the third power of kilopascals. The initial temperature is 20 degrees Celsius. That can be converted to Kelvin by adding 273.15, giving us 293.15 Kelvin. And then we have the final temperature after the cylinder was left in the sun, the final temperature is 50 degrees Celsius. Okay, now I'm going to plug everything into the equation and do the calculations. Then I'm going to rewrite this so that I don't have to deal with the fractions. And that's going to be by cross multiplying. And don't let this number right here intimidate you. This just means it's 1,000 kilopascals, but they wrote it in scientific notation so that you would understand that there are three significant figures. P2 times 293.15 Kelvin. All right. Now we want to get P2 by itself, so we're going to divide both sides of the equation by 293.15 Kelvin. This will leave final pressure by itself and eliminate the temperature unit on the other side. So all we're left with is kilopascals. Now I plug everything into my calculator. And I get P2 is equal to 1,102.336 kilopascals. Looking at the beginning, it looks like I can only have two significant figures because of our temperature measurements. So 1, 2, 0 will not affect the answer, and our final answer is P2 equals 1.1 times 10 to the third power kilopascals. Okay. And this is what we expected. The pressure increased in the cylinder after it was left out in the sun. So the temperature increased, and now the collisions between the gas molecules and the cylinder have more force because they're moving faster. The pressure in a car tire is 198 kilopascals at 27 degrees Celsius. After a long drive, the pressure is 225 kilopascals. What is the temperature of the air in the tire? Assume that the volume is constant. So we're going to assume the volume in the tire is constant, meaning that we use Gay-Lussac's law. What are they asking for? They want to know the temperature of the air in the tire after the long drive. So that's T2. Now we just need to identify the things we know. The initial pressure is 198 kilopascals. The initial temperature was 27 degrees Celsius. And the final pressure of your tire was 225 kilopascals. Let's plug everything in. Now we cross multiply and rewrite. To get the final temperature by itself, I'm going to divide both sides by 198 kilopascals. This will eliminate the pressure on this side and eliminate the pressure unit on this side. And I will plug everything into my calculator and find out that T2 equals 341.0795 Kelvin. So at this point, what I'm actually going to do is put it back into Celsius, because that's the unit that they gave the temperature in. So let's just subtract 273.15 right now. That's going to give 67.9295 degrees Celsius. And we're going to use only two significant figures for that. So 1, 2, and then this 9. We'll bump the 7 up. So the final answer is T2 equals 68 degrees Celsius.